Now that we've discussed the idea of linear first-order equations, let's actually look at some examples. We'll start with a quick summary of the process. We start by calculating our integrating factor, which is mu of x equal to e to the integral of p of x dx. We then multiply through by mu of x. That gives us mu of x times dy dx plus mu of x times p of x y is equal to mu of x times q of x. Or d dx of mu of xy is equal to mu of x times q of x. We then integrate and solve for y, and that gives us that y of x is equal to 1 over mu of x times the integral of mu of x q of x dx plus c. So now that we've outlined the process, let's look at a few examples. So my first one, 1 over x times dy dx minus 2y over x squared is equal to x cosine x. I need to start by putting this into standard form. So I'm going to multiply through by x. That then gives me dy dx minus 2y over x is equal to x squared cosine x. I then need to find my integrating factor. So we'll start with the integral of p of x. We have that the integral of p of x is going to be the integral of negative 2 over x dx, which should be negative 2 times ln of the absolute value of x. However, since I know x is always greater than 0, we're just going to write this as negative 2 ln x. We then have that mu of x is equal to e to the negative 2 ln x. Using properties of logarithms, we'll rewrite that as e to the ln of x to the negative 2. And then using the fact that e and ln are inverses, I just have that mu of x is equal to x to the negative 2. So our next step is to actually multiply our equation through by x to the negative 2. That gives us x to the negative 2 dy dx minus 2x to the negative 3y is equal to cosine x, which can be simplified to the derivative of x to the negative 2y is equal to cosine x. The next step is to integrate both sides. Since the integral of a derivative is just the function itself, we have the left side becomes x to the negative 2y. The right-hand side is the integral of cosine x dx, which is the same thing as sine of x plus c. Finally, we solve for y to get x squared sine x plus cx squared. For our next one, we're going to consider an actual application of why we might want to use this. So let's suppose a rock contains two isotopes. We'll call them R1 and R2, and they belong to the same series. This means that my isotope R1 will decay into my isotope R2, which then decays into stable atoms. We're going to assume that R1 decays into my R2 isotope at a rate of 50 times e to the negative 10t kilograms per second. We're also going to assume that the rate of decay for R2 is proportional to the mass that we'll call y that we have present. So like I said, y is the amount, the actual mass of R2 that we have. So the derivative, the rate that that's changing, the way my mass of R2 is changing, is the rate of creation minus the rate of decay. We know what the rate of creation is. It's 50 times e to the negative 10t. The rate of decay is proportional to the mass. So minus ky, where k is our proportion, our decay constant. We're going to suppose our decay constant is 2 per second, and we also assume that y of 0 is equal to 40 kilograms. So I want to find the actual mass y of t. I want to find this function y. So let's start by writing this in standard form. So I'm going to change the k to a 2 and then add 2y to both sides. That gives me dy dt plus 2y is equal to 50 e to the negative 10t. And once again, I still have my initial condition, y of 0 equal to 40. We know that our p function, the thing in front of y, is 2, so let's start by finding my integration factor. We know that the integral of 2 dt is 2t, So that gives me my integration factor of e to the 2t. So let's multiply through by this. When I do that, I get e to the 2t dy dt plus 2 e to the 2ty is equal to 50 e to the negative 8t once I use my properties of exponents. That can then be written in the simpler form ddt of e to the 2ty is equal to 50 e to the negative 8t. Next, we integrate both sides. The integral of a derivative just gives me the function back, so the left-hand side I have e to the 2ty. And the right-hand side, the integral of 50 e to the negative 8t is negative 25 over 4 e to the negative 8t plus c. We can then divide both sides by e to the 2t, which then gives us that y is equal to negative 25 over 4 times e to the negative 10t plus c e to the negative 2t. We do have an initial condition here, so we do want to go ahead and use that. We know that y of 0 is equal to 40. So I'm going to let t be equal to 0 and y be equal to 40. When I do that, I get 40 is equal to negative 25 over 4 plus c. Solving that gives me that c is equal to 185 over 4, which then gives my final solution. Y of t is equal to negative 25 over 4 e to the negative 10t plus 185 over 4 e to the minus 2t.